Dear student, so today I am going to start this course on the nonlinear function analysis in a formal way. In the last lecture, I just discussed the idea idea and motivation of this course, and I explained a little bit the syllabus of nonlinear function analysis and application. So I told you several things in the previous discussion. So today, this is basically my just starting thing. So this is my lecture 1. So again, I will start with the basic definition of the fixed point. So suppose we have a non-empty set and T is any map from X to X. Okay, so the point X in X is said to be a fixed point of T if T of X equals to X. So that is the given point is invariant under the given transformation of mapping, then such point is called the fixed point of the map. So here this condition means my map should be from same side to the same side. Means we cannot consider the mapping like in this way, means just simply T is a map from X to Y. So of course in this case we cannot talk about the fixed point, because here element from the domain and element from the range should be same. So at least here we have, if we have this condition, so this is not good. But of course in another way we can say, means existence of a fixed point if my T is a map from X to, of course, Y, and Y at least is a subset of X. So my range set should be the, you can say, subset of the domain, or maybe it's maybe intersection of the both, or like this one, X intersection Y. Then in this way we can talk about the fixed point. Otherwise we cannot talk about the fixed point of a mapping if my mapping is simply like non-self mapping. Simply means if you can say X intersection Y is N, means if both are disjoint, then we cannot talk about the fixed point. So at least either we have this condition or maybe we have this intersection, but of course this intersection is non-empty here. This is very important. So this is the basic definition of the fixed point of a operator. So let us see some examples of a fixed point. So first example, if I take X equals to R, this I am going to start with a very simple example, and T is my map from R to R, defined by this rule T of X equals to simply X1 for all X in R. So here we can easily verify or check that 0 is the only fixed point of this. So to find the fixed point of operator or mapping, just we equate this equation Tx equals to X, and then we solve the equation. So of course we do in this way. Just we consider means Tx equals to X, but what is the Tx my rule? X by 2. So this and this implies X equals to 2. So now from here, from the given definition of the function, we can see that T of 0 is 0, means 0 only goes to the 0 under this map. So this is the one example. Here of course there is no other fixed point of this map. Second example, if I consider T is a map, same map, just from R to R, but defined by this rule, T of X equals to x square. Okay, so again in the similar way we can calculate the fixed point of this map tx equals to x square. So if we substitute tx equals to x, so we have the quadratic equation x equals to x square, and then we can solve this equation. So of course we know that 0 and 1 are the two fixed points of this map. So here we have only the one fixed point, here we have the two fixed points, and similarly we can construct the more examples of mappings which has the basically three fixed points and in so way. And if we consider, of course, if we define tx by the x cube, then we have the three fixed point. But if I define tx by the just simply ix, means identity for all x. Okay. So basically, my here t is an identity map, and of course now we can check that every point of the this map, of course, identity map is a fixed point. So here means whole side is a basically fixed point of the given map. So that is again we can say also T of R is exactly same as R under the identity map. So this set is invariant under the identity map. So of course under the identity map is invariant. But of course here only we have the two invariant point. But here whole set is the invariant set. Okay, so one fixed point, two fixed point, we can construct the several examples for three fixed point, four fixed point, and again we construct the example. There is one simple example means of infinity many fixed point. And if I consider this another example, just mapping my same means from R to R. So T of x equals to just x plus alpha. Of course, alpha is some non-zero real number. So now here we can easily check that there is no fixed point of this map, and of course there is a well-known transformation, or you can say mapping, that is called translation map. So if we want to calculate the fixed point, then of course just we can start from here. Tx equals to x. So what is my tx? X plus alpha equals to x. So this implies that alpha is 0, and which is a contradiction because my alpha. And of course you know that when we have a translation map, then every point shift to the next one. Maybe it may be left translation or right translation, doesn't matter. So it may be plus minus sign. It's not a big issue. So from these example, we can say that given map need not possess a fixed point. So question is that under what conditions given map has a fixed point. So my next topic of course is that what are the fixed point theorem. So fixed point theorems are the basically results. So these are the statements, and these results give the guarantee of existence of the fixed point of a given map under the different conditions. Of course, conditions may be on the space, like here we consider simply a set of real number, but in general we can consider any set. So condition may be on the set, condition may be some on the given map T. So these are the mean by the fixed point theorem. So in this first unit, of course, we will focus some classical fixed point results, and which give the existence as well as the uniqueness of the fixed point. Because from these examples one can show that one can see that easily here fixed points are not unique. Of course, in this case fixed point is unique, but here there is no fixed point. So of course, first problem is that when we get the existence, so this is the one problem. Another, when we have the fixed point, whether the given fixed point or map has a unique fixed point or not. So in some cases mappings have a unique fixed point, but in other cases mappings do not have the unique fixed point. Okay, but before going into detail of the fixed point theorem, again we have one question why we are going to discuss this fixed point theory, or you can say it's a part of the nonlinear function analysis and application. Because these fixed point problems are very useful in the several branch of the mathematics. Not in the mathematics, they are also very useful to find out the solution of so many several non-linear problems outside the mathematics, especially in the economics and of course in game theory and in engineering also, especially in the electrical engineering and you can say computer science image recovery problem, fractal geometry also in the fractals. So they have a lot of applications. So as I just mentioned in my last discussion, means the motivation to study the fixed point theory just from the solution of the nonlinear equations. So as again I just start with the basic thing. For example, this is a simple fact from your high school level mathematics. If we have the system of linear equation a1x plus b1y equals to c1 and a2x plus b2y equals to c2. So here we have the system of linear equations in two variables. So of course first we will not go to calculate the solution of the system. First of all we have to check whether the system is consistent or not. Because if system is not consistent, then we cannot solve the system. So of course you know what is the condition to check the given system has a solution or not. So if you remember, this was the condition. A1 upon A2 does not equals to B1 upon B2. So if this criteria met out, then we can say that system is consistent. And when system is consistent means when system has a solution, then of course it may have unique solution or it may have infinity many solutions. So what is the that criteria for this one? So of course A1 upon A2 not equals to B1 upon B2. So again if we remember C1 upon C2, then it has a basically unique solution of the system. But if we consider the basically means bigger system of linear equation maybe in 4 variables or 5 variables, like Ax equals to B, or maybe you can say like C. So here my x is basically just containing 4 vectors. So means here and there is a coefficient matrix of order 4 by 4. So here I have basically 4 variables and 4 unknown. So of course we don't have any such criteria to check. It means very easily whether the system is consistent or not. So here in this way fixed point theory is very useful to check whether the given system is consistent or not. Of course there is a linear system, but we can talk about the non-linear system. Non-linear system, and of course it may be for the differential equation, it may be for the integral equation or partial differential equation, vice versa. So of course we will discuss these applications in the detail once we know what are the well-known fixed point theorems. Okay, so again, so why these are important? And of course again, if I consider the another equation, quadratic equation, ax square plus bx plus c equals to 0. So what is the basically criteria to check the consistency of the solution of this equation? So of course we know that this quadratic equation has a solution or simply roots if my discriminant is greater than or equals to 0, means this is non-negative. So this is the one criteria. If this is negative, then we cannot say about the real roots of the this quadratic equation. So in this way, later on we can construct or consider more complex problem and then check whether that system of equation has a solution or not. So how this fixed point theory is useful in this process, or in process of checking of the whether the system is consistent or not. So just I am going to start with very basic example here. So this is my simple very quadratic equation, x square minus 7x plus 12 equals to 0. Okay, and of course we know that x equals to 3 and 4 are the roots of this equation also. And of course here d is greater than equals to 0, and of course d is positive here because both roots are distinct as well. But of course, but we can formulate this quadratic problem, or of course non-linear problem, as a fixed point problem. So what we can do, we can write this quadratic equation just by this line: x equals to x square plus 12 upon 7. Okay, and now define a map T from R to R by this rule: Tx equals to x square plus 12 upon 7. So this is basically my one of the operator defined from R to R just by this rule, x square plus 12 upon 7. And now we can easily verify that or check T of 3 equals to 3 and T of 4 equals to 4. Means 3 is the fixed point of this operator and 4 is also a fixed point of this operator. It means that fixed point of this equation is basically same as the solution of this my non-linear problem, like this. So it means that once we have the guarantee of the fixed point of this operator t, it means that we have the guarantee of the consistency of the given system, corresponding system. So these are the basically two systems corresponding to each other. And of course, fixed point of this operator are same as the basically solution of this operator. So this is basically very basic or simple, you can say, motivation or idea for the fixed point theory. And of course, we will apply this approach in the more complex problem, especially for the differential equation or integral equation and other problems later on. So this is. So, but this is a very trivial. But this problem was for the just for motivation. It was not for the you can say more technical thing of fact. So, okay. So this is the motivation, because if we know the existence of the fixed point of operator, it means that this implies that corresponding problem has a solution. And fixed point of that operator is same as the solution of that operator. And second thing, a fixed point of this map is unique. It means that this system also has a unique solution. But in this case, for example, there are two fixed points there. That's why there are two solutions of this quadratic equation. Okay. So next, I come to again this example translation map. So from the translation map, at least we know that there is no guarantee of the existence of the fixed point, and there are also so many other maps who do not possess the fixed point of the given condition. Okay, so under what condition we can have the guarantee of the fixed point? So before going to just state the some important results, I am going to just discuss some basic definition. Okay, so this is first my definition. Of course, you know this definition from your maybe differential equation or real analysis course, Lipschitz map. So a map So a mapping T from a metric space X to metric space X. So this I am going to define simply Lipschitz map on an arbitrary metric space. So mapping T from X to X is said to be Lipschitz. If for some constant alpha greater than equals to 0, for when alpha is 0 then it's very trivial, so sometimes some author consider this alpha is positive. So if for some constant alpha greater than equals to 0 we have or T satisfy this condition. So D of Tx, Ty less than equals to alpha times D of xy for all xy from X. So a map is said to be a map from metric space, a self map of course, is said to be the Lipschitz map if for some non-negative alpha or maybe some of course fixed. We have D of Tx, Ty less than equals to alpha times D of xy. So this is called the Lipschitz map. Okay, here from this definition we have some remark or maybe definition. But I am going to write this one as a remark. First one, this Lipschitz maps are always uniformly continuous. That is, they are continuous. So Lipschitz map mappings are uniformly continuous. That is, of course, continuous. This is one observation. And other remark, or maybe you can consider this as a definition also. So here basically my alpha is greater than equals to 0 means non-negative. So if we restrict by this